All right, well, let's get started. So today's webinar is Torque Basics for Assembly. I'm not keen on that name, actually. I think it's more applicable to say it's Torque Basics for manufacturing. Assembly is a little confusing, but we do use torque in assembly, but basically for testing and things like that. So it's a little deceiving, I guess, that we say assembly. So I'm going to say Torque Basics for manufacturing. So my name is John Lytle. I'm an application engineer with Promess. Been working with Promess for about 20 years now, and today I have with me John Derry.
Hi, I'm John Derry. I'm an application engineer with Promess. I've been with the company about 5 years now, and I work on a lot of torque applications from the basic to the more advanced.
Yeah, so what we're going to talk about today, kind of a brief overview, is we're going to kind of define what torque is. Then we're going to explain how we tackle some of our torque applications with our Torque Pro system. And we're going to talk about some of those common applications, how we build a monitoring strategy around that, some of the motion involved. And then lastly, we're going to talk about things to consider when designing a station that may use a device like this to measure or test your particular parts. For the most part, torque's a test type application. And then like we always have, we're going to have our Q&A session at the end where you guys can ask us whatever questions you want to ask us, and we'll do our best to answer that. So let's get started. So what is torque?
So the simplest way to describe torque in the manufacturing or assembly sense is the rotational equivalent of linear force. So it's the resistance of a component to rotate, basically. It's how much effort the component requires to start rotating or continue rotating.
Exactly. So similar to like our other systems that you may or may not be familiar with, but we do a lot in the press fit arena. In fact, that was our last webinar that we did. We have sensing built into this unit as well. So we take a torque sensor and use that to measure the rotational movement in a part. And then we can give you feedback on that, control that, and then put parameters around that to say whether that's a acceptable or not acceptable part. We generally use what we call our Torque Pro system for a lot of these types of applications. And maybe you can explain a little bit about what we have here.
For sure. So just like our press systems, the Torque Pro uses closed loop feedback, utilizing the servo motor and the torque transducer. So we can use either of these. We can either control to a torque or we can control to a position, a rotational position.
Yeah, this particular torque unit is part of our demo system, so it has this knob at the end. We use that, so when you're rotating it, you hold it and you can apply a torque and see it on the screen. But typically, there's going to be a shaft on the end of this that you would couple to, and then that would have the tool or whatever you're using to engage the part with. All that gets fed back to our signal conditioner and our controller, where it's very similar to our other systems in the sense that we have a main controller that handles the motion, all the analysis, and the feedback for that closed loop feedback John talked about. And basically, then we have an HMI software or an editor software where we're allowed to program and that type of thing in that environment to create the actual program that does the actual application for the machine or whatever this is being integrated into. So what are some common torque applications that we do, John?
So one of the most common is breakaway torque, and breakaway torque is the amount of torque required to get a component rotating from a static state to a dynamic state. And a lot of that, we were able to sense or test that a bearing has been pressed in squarely. Say there's a shaft that runs through the bearing. If it's not all assembled correctly, we might see a higher breakaway torque than we'd expect to.
Right, so if it's side loaded or something like that,
Yeah.
you'd pick that up with the torque sensing built into that. So maybe what's an illustration of that if you want to draw on your graph
Absolutely.
here?
So generally breakaway torque can be viewed, if we're saying 0 is roughly here, breakaway torque might come up from 0, fall back down, and then we might move into a more consistent dynamic state at that point. So a lot of times what we'll do then is we would set a window or a parameter rotationally. We might say the first 5 degrees of this curve, we want to monitor and we want to capture peak force or peak torque rather. And that would then be our breakaway torque or torque required to get the component moving.
Right. By measuring that breakaway torque, it gives you at least an idea of how much torque it takes to actually get something moving at that point. And generally, with some of the applications we've been involved with, bearing testing comes to mind right away. It's important to know that because the less friction is better in bearing assemblies and things like that. So understanding where that breakaway is at, how high it is or how low it is, gives an indication of how well that part might work. And ultimately, bearings in particular generate heat, and the less heat you have, which means the less friction you have, they're going to last longer and things like that. So bearings are used in everything. Obviously, we don't have to go into that, but we do a lot of automotive type applications with these torque systems. And bearings one aspect of that. What are some other ones?
The other most common is turning torque, and that goes hand in hand with breakaway torque. Generally, a lot of these applications, we look at breakaway torque and then we monitor turning torque after. So an example of that, the curves would look very similar. We do have to obviously get the part moving, so we still will see, the breakaway torque, and we would see the turning torque after, something like that. Sometimes what we'll do if turning torque is a criteria that we need to look at, we might set some hard limits around it after the breakaway torque has occurred. We might also monitor, say, the peak to peak, the up and low, the high and low, to make sure that's within an acceptable range, as well as compare the breakaway as a percentage to the turning torque. So we do that commonly in a lot of drivetrain and powertrain components to see how much effort it takes to get the part moving and then make sure the effort to maintain the movement is within a reasonable tolerance.
Right. So think like crankshafts in an engine, things like that. We do some cold engine testing with these torque units that we're able to actually measure the crankshaft rotations. You can see the rotations with the pistons moving up and down, and you can plot all that. And like John said, you can then pull off peak to peak values, peak to valley, averages, mins and max, and things like that. Or you can get single points if you see some type of anomaly within the press curve, which is one of the advantages of using something like this. So turning torque is real common. I mean, that basically probably encapsulates 80% of everything we do with these torque systems. One thing I want to say is this is not really a fastening device. So it's really designed for a little more advanced. I know this webinar is torque basics, but it really gets into a little more complex applications and things like that. It's not really designed to fasten a series of nuts onto an end cover, like onto a transmission housing or something like that. Nut runners and things like that are designed more for that. This is a little more advanced from that standpoint. So that's why it has a real load cell built into it. And that's why it has very high resolution as far as the angular feedback for that. But turning torque's real common. We also get into some functional tests and things like that. And what's another one, John?
Another one is lash, or specifically rotational lash, which is the lost movement or clearance in two components, typically a gear set. So a curve that we might see in that aspect, usually we plot this in the negative and the positive direction. So the curve usually starts in the center. We'll go to the far extent, find a tooth, and then from there we'll rotate back to the other extent, find the other tooth. So one difference, a key difference in how we program these, generally the breakaway and turning torque are programmed to look for a degree, and we monitor torque while we go to that degree. The lash generally will be programmed to go to a torque value, and we monitor how many degrees it takes to find that torque in both the negative and positive directions. So a lot of times we'll be able to tell that the distance basically from here to here is now our lash. And there have been some applications I've worked on where we can actually determine that we're center on center with the part, and then we're able to calculate a arc length from this and then convert that to a chord length to give you lash in millimeters instead of degrees, if that's required.
Right, so typical torque applications where you're looking for backlash, and that would be gear, a real common one's going to be different types of gear train assemblies, like an axle that basically has a differential inside of it. So you have various gears inside that, and basically what you're looking for is a tooth-to-tooth distance from one tooth to the other. And I can kind of, show you that. So basically you apply a torque to the positive direction, let's say, capture that angle, and then move to the negative direction, capture that angle, and then you can calculate that distance, and that's what's represented in that graph. So where it slopes and levels off, that would be one point we capture. And then when you get to the rate change on the other side, that's where the delta would be the amount of lash that basically I have. So there's two different types of lash we generally do with our Torque Pro systems. One is what we call our static lash, which is just basically what I showed you. We'll rotate the assembly to various locations and then measure statically, meaning we'll do a tooth-to-tooth comparison there and figure out that delta for the lash value. Then we'll rotate the assembly again and pick out another location. And we'll do that, let's say, 8 times to kind of zone off all the different tooth combinations. And then from that, we gather those lash numbers, and then we'll calculate an average, a min, or a max, or things like that. And that's the more common way, I guess, we do it. But we also have another technique or method that we use with certain applications where customers require a dynamic backlash. Dynamic simply means that we're rotating the assembly. So we're rotating this gear tooth assembly, but applying a load to the input or output and measuring on either the other, the input or output on the other end of that, and then plotting that in a positive and negative direction. And since we can graph that, we can then take the delta of those two graphs and create what we call a dynamic backlash graph. And then we can use that analysis that we've been talking about to basically figure out each individual gear tooth combination and then tell you whether that's acceptable or reject. So dynamic basically is rotating the assembly in one direction, getting all the gear tooth combinations and plotting that and doing the same in the other direction and then taking that delta. That's a little more complex. That's not really basic, but those are things that we generally do with gear trains. So do you have any other examples of possibly what we could, some applications we've done? I mean, I know you do a lot of them out in the field.
A lot of the
recently.
ones recently that I've done for steering assemblies, we might monitor the breakaway and turning torque required to turn a steering column, for example, to make sure that's within specifications. Another one, like John mentioned, we do a lot with engine short blocks where we might be able to pick up piston ring clearances, bearing clearances, all of that based on the turning torque and effort. Once we know what a good part looks like, we can basically set the parameters around a good or known part and then judge all future parts off of that.
Yeah, another aspect of this type of system and why it differs from nut runners and things like that is we also can pair it up with our press systems, and then we can do various types of functional testing where we can apply a load with the press. The press has a built-in load cell to give us force feedback, and then we can rotate a pinion or something like that while applying load to that assembly, and we can calculate efficiency tests and things like that. And to take it a step further, we can do efficiency testing on ball screws and things like that that are used in aerospace applications and various things like that. So basically, it boils down to it's a test type system, not really for fastening and things like that. The closest thing you're going to come to like tightening nuts down and things like that is if that nut is an advanced nut in a design that affects other aspects of how that assembly functions. So like you do some lash testing where you're doing bearing lash and physically pulling on the bearing and then adjusting a nut to hold that lash, right? Maybe
Correct,
tell us a little bit about that.
So we do applications like that where we might preload an assembly with a press, and based on the effort we see from the press preload, we would rotate the Torque Pro a set amount of degrees or a set torque value to get the correct effort on the press side. We also do something very similar with something like, say, a seat bracket or a lever effort, where we might have one object or one press or torque unit throwing a lever while the other side tightens a nut to get the desired lever effort out of the system.
So there's a whole myriad of ways you can do that. And as your gears turn, thinking about applications, like how I throw that in there, you can call our application team because we have 12 application engineers here right now that can answer any of those questions that you guys have or if you have questions about how, the accuracies, things like that, feel free to ask them at the end as well. But you can also test those parts. We have our PDC here at Promess, where a lot of times we're testing for you guys to give you the feedback on how much torque it takes, whether the application seems to fit this device or not, and stuff like that. So feel free to utilize our application team for that. The last part of this webinar that we wanted to go over was things to consider in the torque applications, you guys come across, or what we have experienced out in the field and things like that, working with integrators and end users and stuff like that. So what are some of those things that you need to consider when maybe designing a machine or things like that using a system like this?
The biggest two things I can think of that we need to keep in mind when designing a system to work with the Torque Pro is the size and mass of the tooling and the inertia that is developed with that size and mass to getting it to start and stop as you'd expect. I guess another thing to consider would be compliance in the system. Generally with these type of testing applications, you want the system to be pretty rigid, maybe some compliance to prevent binding, but you almost want to think of the station as a stand or a gauge.
Yeah, so what you're getting at is that if I'm misaligned here when I'm coupled to the device or the part or the assembly that I'm trying to measure or test with, any type of error that you have as we couple to it's going to be measured through the torque sensor. So it is critical that there's some thought put into how we coupled to the device and actually measured the device. Any error you introduce is going to be error reflected in your results. Now, in some cases, we can compensate for that, meaning that if there is high levels of inertia and mass we're overcoming, we can size different gearboxes that can help mute some of that. We can go into some more advanced tuning to hold deacceleration angles and accelerating quickly and things like that. We can tune that out for the most part, but misalignment and things like that generally is tough to do. Other things we can do is as we can do what I'll call like a calibration routine at the beginning. So if we're rotating a large mass that's affecting the torque sensor, I can kind of calculate that as it spins and plot it and then subtract that out of my results. Those are things we can do to handle that, but up front, the biggest thing is to really think of the station as a gauge and design it like a gauge so that it couples correctly and that you don't have a lot of error that's introduced and measured, because these are very sensitive. So that's probably the main things, right?
Yeah. And then again, just keeping in mind that the further out your mass is dispersed from center, the more it affects the Torque Pro. So keeping the tooling as simple as possible to adequately perform the application is always beneficial too.
Right. So that's what we wanted to cover in torque basics for assembly and manufacturing. We're going to get to the Q&A session now, so hopefully you guys have some questions you want us to tackle, and we'll go from there. So here we do. We have quite a few questions, it looks like.
All right. So the first question is, can you attach a torque unit to the end of a robot arm? I guess the short answer is yes. The long answer would be yes, as long as the robot is sized adequately and the torque that we're applying to whatever component will not damage or is backed up correctly to not damage the robot.
Yeah, that would be one of the things that you want to consult an application engineer with. Because we have different mounting patterns too. So if you have a particular way you want to be able to mount that torque unit to the end of the robot, I'd consult with the application team and we can figure that out for you. But yeah, no problem. We've done that in the past. We do that with our presses as well. In fact, we have a whole line of robot presses. So yeah, definitely. Can one controller control more than one torque spindle?
Yes, with our Ultra Pro controller, we can control up to 8 torque spindles, and a lot of the applications I work on have 2 or 3 per controller. It's pretty common.
Yeah, that's actually very common because like I said, and I've kind of been reiterating this through the whole webinar here, is that generally we're doing a lot of test applications, and test applications turn into a level of functional test. So they're doing multiple things to an assembly is what it boils down to. So a lot of times they are multi-axis with presses, torque units, even additional sensing as well. How would this device identify a cross-threaded something? Especially peak torque is reached, but the product isn't fully seated. That's a good question. So basically having the angular sensing and the torque sensing between those two, we generally can figure that out relatively easily. So obviously if you're cross-threading, you're going to not have the same amount of torque that it takes if you're not cross-threaded. So as you cross-thread, you're generally generating more torque because you're starting to, in a sense, broach the threads to some level, or kind of take them out of the actual rotation they should be in. So you're going to generate a higher level of torque. Also, you're monitoring how many rotations you have or how many degrees of movement you have. So in a typical assembly where you're threading something down, you're going to have a certain level of turning torque, right? Like he explained here in the graph. And then as you get to the end of the threads and that nut or whatever it is bottoming out to fasten something together or hold something together, you're going to have a torque and spike at that point. And that's basically going to have the a higher torque level. So you'll be able to easily identify that with just putting limits around whatever angle you have that higher torque at. If you fall outside of that, then that would be considered a cross thread. That'd be one way to do that. You're going to see that visually, and then you're going to attack that with some curve analysis as far as figuring that out where it's at. You can also have a real-time limit in there. If you achieve higher torque before you reach X amount of angle, then you can stop the system at that point and back it right out. And then do what you need to do after that. How does the torque unit compensate for fixture torque?
So like John mentioned, if you have a fixture or say you're running a dial machine that the Torque Pro engages with different stations, we can actually rotate each station individually, record the torque it takes to just rotate the station without a part in the nest, for example. And then we'll save that and have basically a compensation factor. So if we know it takes, say, 2 newton meters to rotate just the nest, we can subtract 2 newton meters from the reading we get from the part. And that's usually done over multiple rotations. Sometimes they'll run that every shift or once a day or something like that, just to make sure it stays updated.
Yeah, kind of call that a zeroing routine.
Yeah,
sort of.
zeroing routine or a master routine sometimes.
So one important thing on that is that, keeping in mind that a lot of applications we're measuring torque in the positive direction and the negative direction. So that's positive torque and negative torque. So it's not only important to understand the torque in the how much torque there is in the machine without the part in there in a positive direction, but also in the negative direction. So it's not just understanding what that is, but it's also zeroing that or balancing that. Because there are other effects that happen. Torque can be complicated to understand some of that. So not only how much torque it is, but also you have to balance that and then zero the sensor based off how much there is in one direction versus the other direction. And we have developed over the years some pretty simple solutions for that, canned routines we use in our software and our controllers that we use for that type of stuff. So they're telling me there's no more questions. So at that point, that kind of concludes this webinar. Thanks for watching. You can contact us at 810-229-9334 or at promessinc.com. I'm sure you guys probably know that already. And I look forward to you joining us for our next webinar, which is November 17th. And this is not necessarily an educational one like we've been doing. This is more of a thought leadership type and talking more about where the industry's going with smart devices and simplifying motion and sensing in the assembly arena. And I think we titled that Simplifying Motion and Sensing with Smart Devices. So I look forward to you guys joining us November 17th, and thanks for joining us for this one.